Okay, hello. So in this video, I will be covering the paper displayed here, which is called Arbitrarily Complete Bell State Measurement Using Only Linear Optical Elements. This paper was written by W.P. Grice, and it appeared in PhysRev A in 2011. So the abstract begins, a complete Bell state measurement is impossible with only linear optical elements. Most schemes reach 50%. A pair of ancillary entangled photons raises the success rate to 75%, and 2 to the n minus 2 ancillary photons raises it to 1 minus 1 over 2 to the n. Now, the protocol that's presented in this paper is going to use ancillary entangled photons to create what's called this arbitrarily complete Bell state measurement. That means that, as you can see by the reported success rate, we can get arbitrarily close to perfect Bell state discrimination with more ancillary photons. The fact that this protocol only uses linear optical elements is important from an engineering perspective because those components are much easier to manufacture. If you were to relax this assumption and use, for example, active elements or nonlinear media, there are certainly other protocols which could give complete Bell state measurement. The technique presented in this paper, along with related ones, came to be known as boosting in the fusion-based quantum computing literature because it essentially boosts the success rate of a primitive computational operation in that area known as fusion, which is based on Bell state measurement. The first thing we're going to do in this paper is explain why it's the case that when you restrict to only linear optical elements, you are essentially limited in your success rate for Bell state measurement. This is a consequence of some fundamental features of linear optical systems. So first of all, what are the Bell states? So you can write them as vectors like this, and they are essentially states defined over 2-qubit systems that capital Phi plus or minus and capital Psi plus or minus. They can also be written in a computational space as cats over qubit states, and they assume values like 0, 0, plus or minus 1, 1, and 0, 1, plus or minus 1, 0. These states are super important across all of quantum information for a number of reasons. They're the smallest states that expose non-classical correlations, which are important for non-locality studies. They are maximally entangled, and they're used in a number of protocols like teleportation and entanglement swapping, not to mention fusion in fusion-based quantum computing. Let's now describe what it means to perform a Bell state measurement. Consider a quantum system made up of a grid of qubits. Suppose that you want to perform a Bell state measurement. The Bell state measurement occurs over 2 qubits. An arbitrary quantum state can be decomposed in the Bell basis over those 2 qubits. The algebraic expression looks like the following. This is because the Bell states are a basis spanning that 2-qubit space. A Bell state measurement will project those 2 qubits into one of those states. A Bell state measurement will collapse those 2 qubits into one of the Bell states. The rest of the quantum state will be equal to either psi 1, psi 2, psi 3, or psi 4, corresponding to whatever outcome was measured. Measurement in the Bell basis is mathematically modeled by joint measurement in the XX and ZZ Pauli operators. The ZZ operator returns outcome plus 1 for the phi states and outcome minus 1 for the psi states, while the XX operator returns outcome plus 1 for the plus states, either psi or phi, and minus 1 for the minus states. For this reason, we can shorthand refer to the the operators as the family and sign operators. Now we'll talk about how this is implemented in an optical system, but this is just the sort of mathematical backdrop for a Bell state measurement. Now it might be worth mentioning why the ZZ and XX operators correspond to a Bell measurement. Well, the reason is, and this is really not within scope of the video of boosting, so I'm not going into it in a lot of detail, but the reason is that if you decompose these operators into their eigenbasis is the Bell states. Now we move on to how the Bell state measurement is implemented in a passive linear optics setting. We're calling this the Bronstein-Mann scheme because there was a paper that basically outlined this protocol. The scheme is employing a 50-50 beam splitter to perform the Bell state measurement. As you can see, the only components here are passive and linear. The detectors are assumed to be able to resolve both photon number and polarization. The beam splitter is only going to mix the spatial modes and leave polarization untouched. So let's now model the effect of this circuit here on Bell states, and we'll start to see why this is getting us toward a Bell state measurement. So first of all, the 50-50 beam splitter has the following input-output relation. We can also express the Bell states in terms of their optical implementation in dual rail here. So if we encode them in the polarization of a photon, this is what they're going to look like. So the psi states are a superposition of a horizontally polarized and a vertically polarized photon, and the phi states are a superposition of two horizontally polarized and two vertically polarized photons. There was actually no reason to separate psi here but not phi. But what we're going to do is subject these states mathematically to the input-output relation implied by the 50-50 beam splitter, and this will give us the output. Now, conceptually, in order for Bell state measurement to work, we need the outcome of the measurement at the detectors in terms of the click patterns to map back definitively to one out of the four Bell states. For this to happen, we need each Bell state to impart a unique detection pattern on the detector network. So when you design the Bell state measurement, you're trying to create discrimination between the Bell states in the click pattern. So what we're trying to verify here is whether the 50-50 beam splitter and detector network setup here gives a unique detector pattern for each Bell state. Before we write the input-output relation involved in the Bronstein-Mann scheme, we should refresh ourselves on what happens when a pair of photons is incident on each input mode of a 50-50 beam splitter. If the photons are indistinguishable, they exhibit a behavior known as bunching. This is a central feature of what's known as the Hong-O-Mandel effect in optics, which is outside the scope of this video, but which I will make a video about in the future. Other times, the photons may exhibit anti-bunching, where they always exit at different output ports. So with bunching, the photons always exit the same output port, and with anti-bunching, they always exit different output ports. If the two photons that are incident on a beam splitter are the two photons of a Bell state, you can run the input-output relations that are imposed by the beam splitter and identify instances of either bunching or anti-bunching. If we look at the psi plus state, we see an instance of bunching because the incident photons either both exit in spatial mode 1 or they both exit in spatial mode 2. For the phi state, we also see an instance of bunching, since the photons both exit in the same spatial and polarization mode. For the psi minus state, we see an instance of anti-bunching, because the photons exit in different spatial modes. Now that we understand what we should expect from this beam splitter setup, we can look at the full interaction of the Bronstein-Mann experiment with Bell states. So let's consider the situation where the psi plus state comes in. As we mentioned from the equation, the psi plus state will exhibit bunching, and it will click either both H1 and V1 or both H2 and V2. The psi minus state will exhibit anti-bunching and click either both H1 and V2 or both V1 and H2. The phi plus and minus state will both click one of the detectors, either V1, H1, H2, or V2 individually, because two photons will hit those detectors. The phi state is unresolvable because the quantum state only differs by a relative phase, as you can see from the mathematical equation. The relative phase is not something that resolves in the detector patterns. In both instances, one detector will click with a two-photon state. Let's look at the equations a little more closely. The psi state is converted to these states at the output. The phi states convert into these states at the output. Notably, the photon number parity, which can be detected by assumption, is odd in the case of the psi family and even in the case of the phi family. This is why, despite the inability to discriminate between phi plus and phi minus, there is still an ability to discriminate whether the state that was incoming was psi or phi. Analogously, the scheme always reads ZZ, the family bit, from photon number parity. It does not successfully read XX, the sign bit, because it cannot discriminate phi plus and minus. This is why Bell state measurement is said to only work 50% of the time. Theoretical results by Weidmann-Uron and Calsamilla-Lütkenhaus proved that this 50% success rate was optimal for passive linear optics under the assumption of auxiliary modes in vacuum, no ancillary photons, and no feed forward. A complete measurement is possible only by leaving that arena, either nonlinear optics, hyperentanglement, or feed forward. So the proof says nothing about relaxing its own assumptions about what entangled ancillas could do, because entangled ancillas are leaving the arena. This is why conceptually there was an open door. The 50% no-go assumes that auxiliary modes are in a vacuum state, so no ancillary photons. It also assumes no feed forward. If you relax this and feed in entangled ancillary photons in the auxiliary modes, then the theoretical limit of 50% no longer applies. So how far past 50% can entangled ancillas take us? The rest of the paper is a demonstration of one protocol, which takes us to a success rate of 1 minus 1 over 2n for 2 to the n minus 2 ancillary photons.